Hello students. Next we're going to talk about solar savings fraction. This is a wonderful calculation that helps you figure out how much it's going to cost to heat your home before you ever build it. It also tells you what percentage of the sun's rays will contribute to the heating of your home. In other words, how much of your home will be heated by your solar design. This calculation was designed by Doug Belcom. He's a senior fellow with the National Renewable Energy Labs. He has since created software that allows these calculations to occur at much faster than what we could do them. But I wanted to show you how the calculations work so that you could get an in-depth understanding of where the calculations come from. Now, even in very cold climates, you can design a super insulated solar home that needs almost no backup heat at all. I've seen houses that are heated in Canada only with light bulbs. I've seen houses in Upper Michigan that use a little bit of wood, where the people can actually go away during the winter and don't have to worry about the pipes freezing. So the charts here that show you the percentage that you can get of the sun's rays are actually kind of conservative. But that's okay, because it'll give you an idea as to what kinds of systems perform better. And then if you want to go ahead and get the software, you can. But you can also just learn the design principles of solar here and apply them to your own projects. If you're a professional, I strongly recommend that you get that software, because it'll give you the opportunity to do multiple runs very quickly and start to see the patterns of where you're going to get the most output for your solar design. But as you know, our book that we're using in class gives you the basic principles. Now we're just going to dig in with some calculations in more detail. And I'm here to explain them to you because they really aren't that difficult. So please go to week 5 of your course on the assignments page and open up the handout that says solar savings fraction. You'll see on that handout there's some verbiage on the top. You can pause the tape now if you need to go open it up. Okay. You'll see some verbiage on the top that talks about solar savings fraction. And then you scroll down and it describes the house that we're going to use as the example for a little bit. And then it starts to talk about NLC. NLC stands for net heat loss coefficient. So I'm going to show you on this camera the handout. That's the handout, and here's the part that I want to talk about now, the building net heat loss coefficient. And you'll see what it really does is it calculates the heat loss. Here's the units over here. In BTUs per degree day. That's the heat loss. And it gives you the heat, shows you how to calculate the heat loss of the walls, the roof, the east, west, and north windows, the perimeter of the slab. Most of the heat loss out of a slab goes out the edge. Out the basement, out the floor, if you have a crawl space, and then the heat loss due to air infiltration. So, you will notice on that worksheet that there are some similar items to what we learned when we learned the basic air infiltration and heat loss calculations from conduction. So, for example, in the wall calculation for the heat loss out the walls, you see the 24? That's similar, right? That same 24 that stands for 24 hours a day is in the roof calculation, the east, west, and north calculation. And then you'll see the slab calculation. It's no longer 24, is it? It's 100. There's an adjustment there of a multiplication of 4. In the basement, there's an adjustment there too of a multiplication of over 10. Crawl space again is 24. Now, we'll get to air infiltration later. Those adjustments for the slab and the basement have to do with lots of calculations that looked at where does that heat loss go out the slab, where does it go out the basement, and how do we account for it. You could say the factor of 10 has to do with the height of the basement walls. You could say that the perimeter of the slab has to do with some kind of calculations about the edge of the slab. But what's important to know is that somebody's done all of that work with lots of computer modeling. So the next column you'll see is the area column. Let me show it to you. It shows the area of the walls, the area of the east, west, and north windows, now the area of the roof. But when we get to the perimeter of the slab, we're no longer looking at just the, we're looking at the edge of the slab. That's really where the heat loss is. So in this case, you're going to measure the length of each of the edges of the slab and add them together. So if you have a house, that is the house that was given to us in the example, and you add all the length of the slab together, you end up with 130 linear feet. That's what goes in there. Once again, we would use the same figure for basements, and if we had a crawl space, we would just do the area of the floor. So, what comes next? See the little slash there? Everything gets divided by the R value. Do you remember from the conduction heat loss equation that the R value, that 1 divided by the R is the U value? So really, these equations are very similar to the U times A times the U times the A times the 24. The degree day is missing because our answer is in BTUs per degree day. Notice that when you're doing the calculations for the basement and when you're doing the calculations for the slab, there's an extra number, plus 5 or plus 8, that you add to the R value to take into account the insulating value of the earth. So hopefully that explains to you how you would run these numbers so that you can end up with your BTUs per degree day. The BTUs per degree day heat loss out this house, out all surfaces you'll notice except the south-facing windows, is known as the net heat loss coefficient. It's also known as the NLC. Okay, let me describe the last item here in this chart. That's air infiltration. Remember our calculation for air infiltration, 0.018 times the volume times degree days times 24 times the air changes per hour. Well, 0.432, that first number, 0.432 is 0.018 times 24. So that's where that number comes from. The volume you know, times air changes per hour. ADRs has to do with the air density ratio. If you live up in the mountains of Colorado, you have to take into account that the air is less dense. So you calculate those out, just plug in the numbers, crank them out, and you'll get your net heat loss coefficient. In the next video, we'll talk about the load to collector ratio and the solar savings fraction. We'll also look at how you can calculate how much it costs to heat the house before you even build it.